Hello everyone, I'm Norman Wahlberger. In this video and the next, we're going to look at our 10th famous math problem. The question of the integral of x to the n. Now, some of the problems in this series are going to be more important than others. I hope they're all interesting, but definitely some of them are of greater significance both historically and practically. And that's certainly the case with this one, which is going to be in the top 10 in terms of importance in our series. So we're talking about a very fundamental formula for calculus. It's a formula that all students of calculus learn. In fact, there are really two fundamental formulas in calculus, and I call them I and D. And one of them is the basic formula for integration, and the other one is the basic formula for differentiation. Now we're talking about integration and differentiation of a very fundamental kind of function, the basic power function x to the n. So the first of the fundamental formulas, the one that we're mostly interested in today, which is this one, is the integral from 0 to a of x to the n dx is equal to a to the n plus 1 over n plus 1. And that formula turns out to be valid for n, an arbitrary integer, which is not equal to minus 1. We can see that if n is equal to minus 1, there's obviously a bit of a problem, because then on the right-hand side we're dividing by 0. The corresponding formula for the differentiation is that the derivative of x to the n, d by dx of x to the n, is n times x to the n minus 1. And that's valid for n, an arbitrary integer. So a famous math problem 10, which is what we're interested in today, is to define and establish this formula I for natural number values and 0. So for n equals 0, 1, 2, 3, 4, and so on. And notice that there's really two aspects to this problem. One aspect is to define what the integral actually means, and the other aspect is to actually establish the formula once we've understood what it means. What's the difficulty level? I assign it a difficulty level of 8, which is probably a big surprise to many of you, because you will believe that this is already a well-known solved problem. The difficulty level 8 is saying that I think this is an unsolved problem. Okay, and it's rather a challenging unsolved problem. So there's something rather unorthodox here in my point of view. What I'm going to hope to do is to actually solve this problem for you. So I'm going to give you a novel and interesting approach to the integral and to the evaluation of this formula. This approach that I'm going to show you actually opens the door to a new way of thinking about calculus, what I call the algebraic calculus. All right. So in my Math Foundation series, I'm trying to lay out foundations for mathematics, and I talk a lot more about this thing. This derivation of this formula is going to play an important role in our setting up of the algebraic calculus. So certain doors are going to open to us with our understanding of this fundamental problem. If you open a modern calculus or analysis text to the section on integration, you will find there certain assumptions that are mostly uniformly believed these days at the beginning of this millennium. Here are 4 standard assumptions that I'd like to make explicit, and I'd like to call into question the validity of these assumptions. All right, the first is that integration actually requires a prior framework of real numbers. That in order to set up integration, we need, first of all, to understand irrational numbers, and we need to model the continuum as the so-called real numbers. The next assumption is that integration is a generalization, an extension of a prior theory of area. Another important assumption is that integration requires a theory of limits, that it's intimately connected with infinite processes. And these infinite processes are encoded in terms of limits, and that's why we require real numbers to be the limits of these infinite processes that are involved in the definition of the integral. And it's a standard dogma that integration logically follows differentiation. Almost all calculus texts start with differentiation, which is deemed to be simpler and more fundamental, and then integration is often introduced as some kind of inverse procedure to differentiation. My attitude to these assumptions? No, 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 no. Okay. Each of these assumptions is actually highly dubious and questionable. And I'd like to suggest to you to plant in your minds the idea that perhaps, just possibly, these assumptions are wrong. Okay? That they represent a misunderstanding of the real nature of integration. So to fully explain that, it's going to take a lot of time, and that I will be doing that in my Math Foundations series. But we'll see some of that in our novel approach to the integration, which doesn't require real numbers, which doesn't rely on a prior theory of area, which does not involve infinite processes and limits, and which does not require having established differentiation first. So I'm going to show you an alternative way of thinking about things that avoids these assumptions. So in this kind of situation, when we have a little bit of divergence of opinions about which way to go, it's often a good idea to look at the historical record, to see how the development of ideas has changed over time, and how our particular position is a consequence of earlier pioneers' work. So we're going to look at some examples here. Let's start with the simplest one, when n equals 0. In that case, the formula reads that the integral from 0 to a of 1 dx equals a. And the meaning of it is this, that here is the usual xy plane, and the function that we're talking about, the polynomial, is the constant polynomial 1. And so the usual interpretation is that we're talking about the area underneath this graph from 0 to a. We're talking about that red area there. Of course, that's the simplest kind of area. It's the area of a rectangle. And so the area we all know is the base times the height, a times 1, which is a. So the formula is obviously valid in that case, at least when a is positive. If this number a happened to be a negative number, well, then our area would actually have a negative value, and then maybe there'd be a little bit of a question about what the right interpretation of the integral is. All right, now let's look at the next case. When n equals 1, we're talking about integrating a linear function, the function x. Here's the graph of x. It's just a straight line, the slope 1. So the integral from 0 to a of x dx, we're talking about the area from 0 to a under this graph, under this line. Well, that's the area of a triangle now. And the triangle's base and height are both equal to a. So according to Euclid's formula for the area of a triangle, the area is going to be base times height divided by 2, which is a squared over 2. And that's the special case of the formula when n is equal to 1. Remember, it's a to the n plus 1 divided by n plus 1. So when n equals 1, it corresponds to well-known Euclid's formula for a triangle. All right, so now let's have a look at the more interesting case when n is equal to 2. The formula then is that the integral from 0 to a of x squared dx is a cubed over 3. And it's a result that follows almost immediately from the quadrature of the parabola obtained by Archimedes, described in our famous math problem number 6. So if you haven't watched that video, and perhaps you'd like to have a look at it. Here's the parabola y equals x squared. We're interested in the area under this parabola from 0 to a. And I note that when x is equal to a, then the y-coordinate here has got to be a squared. So there's a box here of base a and height a squared. All right, so we can think about this area under the parabola in terms of two pieces. There's the piece that's contained in this sort of tangential triangle. Okay, so the triangle formed by the tangent at the origin and also the tangent at this point here. And one of the things that Archimedes realized, that we established in the famous Math Problem 6 video, is that this tangent and this tangent here meet at a point which is halfway between these two. Okay, so that in fact holds no matter which 2 points on a parabola you choose. If you choose any 2 points on the parabola and look to see where the tangents meet, then the x-coordinate of that meeting point is exactly the midpoint of the x-coordinates of the two places where you're creating the tangents of. So in terms of the coordinates, that coordinate is a over 2. Okay, so the area that we're interested in, the red area, is consisting of this sort of piece here, this arc of underneath the parabola but contained inside the tangential triangle, plus the area of the triangle ABC. Now what do we know about this arc here? Well, Archimedes' result about squaring the parabola was that the area above the parabola contained in this tangential triangle was 2/3 of the whole triangle's area. That means that the area underneath the parabola contained in the tangential triangle will be 1/3 of the area of OBC. So this area right here, up to the tangent, that area there, is 1/3 of the triangle OBC. That's a direct consequence of Archimedes' formula. So to that we have to then add the area of ABC to get the entire area. Okay, what is the area of OBC? Well, it's a triangle with base a over 2 and height a squared. So its area will be a cubed over 4. 1/2 base times height. And that we have to divide by 1/3. And then we have to add to that the area of triangle ABC, which is also a cubed over 4. It also has base a over 2 and height a squared. We add them up, we get a cubed over 3. So the formula for n equals 2, this fundamental integration formula, is basically known to Archimedes. This is a consequence, an immediate consequence, and essentially equivalent to Archimedes' quadrature formula for the parabola. Now, the kind of geometrical approach that Archimedes took is quite foreign to the way most calculus texts these days present the subject. So even though Archimedes' formula for the integral of x squared is, in some sense, the earliest serious formula in calculus, it's almost never presented to students. What they rather see is an approach to area involving little rectangles built up under the curve that we're trying to find the integral of. So this is another method that I would like to describe, and let's start with a very simple case when n equals 1, which we already know. But suppose we want to calculate the area under the graph y equals x from 0 to a in the following way, that we're going to divide the interval 0a into n equal subintervals. So we're going to divide it up into n little pieces, so each piece will have width a over n. So the coordinates here are a over n, and then the next one will be 2a over n, the next one 3a over n, and so on, all the way up to this second last one, n minus 1a over n, and finally a by itself. All right, now over each of these subintervals, the idea is to build a rectangle that goes up until it hits its head on the curve. Okay, so at this interval here, for example, we're going to build a rectangle whose height is also a over n, because that's the y-coordinate at this leftmost point. This interval just gets a flat 0 area rectangle because that's the smallest one that we can fit in. So we have this sequence of rectangles, each increasing arithmetically in height, up to this last one, whose height is given by the y-coordinate at this second last point. So it's up to n minus 1 times a over n. And the idea is we're going to add up the areas of these rectangles. And that's going to depend on n, the number of subintervals. But then we're going to see what happens when n is a rather large number. In that case, we expect these rectangles to better and better approximate the area under the graph. Alright, so in this case it's relatively simple to add these areas up. So the area of all the rectangles is what? Well, each of these rectangles has a base a over n, so that's a common factor we can pull out. Then we just have to add together the various heights. The first rectangle has height 0. The next rectangle has height a over n. This second one here has height 2a over n. All the way up to the last one, this one here, whose height is n minus 1 times a over n. Base times height. The heights are increasing. We have to add them all up. Okay, there's a common factor of a over n here, which we might pull out to give us a over n squared. And then what's in the bracket is somewhat simpler. We just have the sum 0 plus 1 plus 2 all the way up to plus n minus 1. So it's an arithmetic series. And there's a well-known formula for this that was well known to the ancient Greeks, that if you add up the numbers from 0 or 1 up to n minus 1, then you get n minus 1 times n over 2. So for example, 1 plus 2 plus 3 plus 4 plus 5, so if n happened to be 6, and n minus 1 would be 5, then this formula would be 5 times 6 over 2, which is 30 over 2, or 15. And 1 plus 2 plus 3 plus 4 plus 5 is indeed 15. Okay, so once we've gotten this formula for it, we can simplify a little bit. One of these n's will cancel with this one here. So we get a squared over 2. And we have an n minus 1 still on the top and an n on the bottom. So we can see this is almost a squared over 2, but not quite, because n minus 1 is a little bit less than n. But if n is rather large, like 1,000 or 1,000,000 or 1,000,000,000, then this ratio is pretty close to 1. And it's approaching 1. The bigger n gets, the closer this approaches 1, which means that the sum of the rectangles is approaching a squared over 2. So in some kind of limiting procedure, we can determine the area under the line to be a squared over 2. Of course, in this case, the area is just the area of a triangle, which we can get simpler in another way. But it illustrates an important idea, an approach to calculating areas, which works more generally. So now let's have a look at this new method of using rectangles built up under a curve for the case n equals 2. Again, it will turn out that we have to go back to Archimedes. Alright, so here's our graph y equals x squared again, from 0 to a. And just as before, I've divided the interval from 0 to a into n equal pieces, each interval of size a over n. So this interval, a over n, so that coordinate is a over n, and then that coordinate will be 2a over n, 3a over n, and up to n minus 1 a over n, just as in the previous example. And now we build rectangles above each of these subintervals, and the heights of the rectangles are determined. Well, we just go as high as we can until we bump our heads on the curve. So for example, at a over n, we're going to go up how far? Well, just the y-coordinate associated to a over n, and so that's a over n squared, because the curve is y equals x squared. So here the y-coordinate will be 2a over n squared, and here it will be 3a over n squared, and here it will be n minus 1 a over n all squared. The right point all the way up to a squared. All right, so what we're going to do is we're going to add up the areas of these rectangles. There are n rectangles. Each of them has base a over n. What are their various heights? Well, the first height is 0. The next height is a over n squared, and then 2a over n squared, and then 3a over n squared, all the way up to the last one whose height is n minus 1 a over n squared. And just as we did last time, we can pull out a common factor. The common factor here now is a squared over n squared. So when we pull that out, we get an a cubed over n cubed out front. And what's inside the brackets is then 0 plus 1 squared plus 2 squared plus 3 squared, all the way up to n minus 1 squared. So we're in a similar situation as we were in the previous case, except that now instead of having to sum 0 plus 1 plus 2 up to n minus 1, we have to sum 0 squared plus 1 squared plus 2 squared all the way up to n minus 1 squared. That's a trickier business. And there's a formula for it. The formula for the sum of the squares up to n minus 1 squared is this. It's n cubed over 3 minus n squared over 2 plus n over 6. And where does that formula come from? It comes from Archimedes. Archimedes established this fundamental formula. And he would have thought geometrically, because the ancient Greeks thought geometrically. So he would have thought of this as, well, it's a bunch of squares, 1 squared, okay, then there's 2 squared, that's like a 2 by 2 square, and then a 3 by 3 square. And you can think of maybe having little cubes and stacking up cubes and getting some kind of three-dimensional pyramidal shape. And with a bit of geometrical insight, you can maybe put some of those together to find a formula for this geometrically. So he would have done something like that to establish this formula. In fact, he didn't establish it in this context. He established it in a somewhat different context. He was working with a spiral, and this same formula came up. All right, so what can we do with this formula once we've got it? Well, we can now simplify this expression. Because this n cubed here, well, we can divide each of these terms by n cubed. We'll get a cubed on the outside, and now this will become just 1/3. And when we divide here, we're going to get minus 1 over 2n. And when we divide here, we're going to get plus 1 over 6n squared. And this makes it clear what's going to happen to this thing as n gets large. As the number of intervals gets bigger and bigger, these rectangles are going to start approaching the area under the curve. And as n gets big, this 1 over 2n term is going to get small. And the 1 over 6n squared term is going to get even smaller. So once n is like 1,000,000 or something, this is almost negligible. This is very negligible. And the whole thing is approximately a cubed over 3. So we can see that that's what it tends to as n gets big. And that's the formula that we wanted. That's the same formula that we obtained from the quadrature formula of Archimedes. So these two methods agree. Okay, as an exercise, you might like to check Archimedes' formula for some small values of n and have a go at trying to prove it. Probably most fun if you try to find some geometrical interpretation in terms of maybe little cubes, try to prove that formula. All right, so this kind of computation, this understanding, would have been in front of the 17th century mathematicians. And that's where we go to now for the next development. We're now looking at what happens if we jack up this power to go from n equals 2 to n equals 3. That's a big jump because we no longer have a quadrature formula like Archimedes gave us for the cubic. Cubics are quite different from conics geometrically. Okay, so the generalization of the formulas for n equals 0, 1, 2 that we've established basically in antiquity is this one here. This is the basic formula that we're trying to establish. The integral from 0 to a of x to the n dx equals a to the n plus 1 over n plus 1. This is known as Cavalieri's formula. It is a formula of an Italian mathematician, Bonaventura Cavalieri, who lived from 1598 to 1647. He was a professor at the University of Bologna, and in fact he was a student of Galileo. This is a very important formula that he established. But he only in fact gave arguments in support of this formula for special cases. And he had to work out the special cases one by one in a rather painstaking way. So he proved it for n equals 3, and then he proved it for n equals 4, and then n equals 5, all the way up to n equals 9. And his argument, well, it relied on the binomial theorem. It involved a kind of a idea of infinitesimal rectangles or indivisibles. So he thought about slicing an area. This is, for example, y equals x cubed, and we're trying to find the area from 0 to a under y equals x cubed. He thought in terms of slicing this in terms of little infinitely thin rectangles. And there was some kind of geometrical argument sort of comparing this area to this area there. The argument was not entirely watertight because the nature of these infinitesimal rectangles was a little bit dubious. Okay. His work was followed by more algebraic treatments. So many prominent mathematicians recognized the importance of this formula, of course. And notably Wallis, very important British mathematician, Fermat, Roberval, Torricelli, who was a student of Cavalieri. Around the 1640s, they established the formula for general n in various ways and with various levels of rigor. Okay. But sort of by the mid-17th century, this was now a well-established formula that was really a foundational tool for calculus, the calculus that would then be built by Newton and Leibniz. And of course, maybe we can say that Newton and Leibniz did not discover calculus. This is an exaggeration. They were very important contributors, but there were also prior contributors. And any honest assessment of credit has to give credit also to the ancient Greeks, notably Eudoxus and Archimedes, who really set up many actual ideas of the calculus almost 2,000 years before these gentlemen came along. Despite these very prominent successes of the 17th century in establishing Cavalieri's formula, there were still serious logical problems remaining with the definition of the integral. The actual question of what exactly does this thing actually mean? So everyone had an intuitive kind of physical idea of the area under a graph, sort of extrapolated from the idea of areas of rectangles, triangles, and polygonal figures. But to define precisely what this was, that was a much trickier problem. And it's still an essential problem in calculus texts today in the year 2013. It's an essential problem that is still there. Okay, so the problems include the following. First of all, there's always this problem of the nature of the continuum. The establishing of the real numbers and arithmetic with real numbers, which is the foundational problem to set up everything. Turns out that that's much harder than people imagine. And you can see that by going to your calculus text and trying to find a place where the theory of real numbers is really set out completely, clearly, and coherently. You will not find such a chapter. Okay? And there's a good reason for it. It's because it's basically impossible. Then there's inconsistent usage of limits. So the theory of limits with epsilons and deltas, if you do it formally, actually has logical problems associated to it. And these logical problems have to do with the actual sort of infinite specifications required in the definition of epsilons and deltas. So I'm going to talk more about this in the Math Foundation series. I don't want to go into great detail. But let's just say that there are problems with limits, even simple limits like limits of a function as x approaches a value. But when we go to the integral and the definition of the integral, limits are also used. But there is then an additional very serious problem in that the limits involved in the definition of the integral are of a much different kind than the limits of a function as x approaches a certain value. So you may have already established and feel confident about what limit of f of x as x approaches a means. But that doesn't prepare you for the kinds of limits which are introduced in the definition of the integral. The problem is that the limits there are over partitions of the interval 0 to a. It turns out that it's not sufficient to just divide the interval into n equal pieces, as perhaps the previous examples suggest. Wallis and Fermat already realized that in some situations it was more advantageous to divide the interval in a geometrical series way rather than an arithmetical series. So that involves then having to widen our scope and think in terms of partitions as norms of partitions go to 0. And the establishing of such a limiting theory for that kind of limit is almost never done in calculus texts before the actual definition is used. There's very serious problems here. And you can open up any calculus text almost, and those problems are visible. They're right there. You can see them. Then there's this lack of a prior theory of area. If you're going to build up integration as a generalization of area, it behooves you to have a theory of area of polygonal figures first. So the chapter before the chapter on integration ought to be a chapter on areas of polygonal figures. Turns out that that's considerably more subtle than people imagine. It's not just area of rectangles and area of triangles. It's more complicated than that. And that theory is largely absent from our modern treatments. Very big omission. Then there's ambiguity over the role and nature of functions. We write down things like f of x. We don't actually say, well, what exactly is a function? Computationally, in terms of computer science and program, what kind of programs are we allowing here and what kinds are we not? And then there are all kinds of technical difficulties which are usually finessed. Right? So it's easy enough to give a picture when, say, the graphs are increasing and nicely continuous and so on. But when the graphs are going up and down, when the graphs go under the x-axis and become negative, then there are all these technical difficulties that arise if you're going to do things carefully. And most first-year students do not see these technical difficulties. Okay, they are finessed. And then once you get to an analysis course in third year or something like that at university, then typically one already assumes that the theory of integration is well known. So it's a bit of a shell game, right? We've done it then, we're going to do it there. And no one actually pins the logical problems down. All right, so I'm going to talk more about these issues. I'm going to, make all of these objections very clear eventually in my Math Foundation series. So if you're interested in these things, that's the place to find out all about these things. Although it may take a time before I get around to all these things. So let me have just a look at one particular of those problems that I mentioned. Let's talk a little bit about the theory of areas, which is largely an absent theory in modern mathematics, unfortunately. It's a problematic subject that goes even back to Euclid. So even Euclid's treatment of area was highly suspect. The problem with area is that it's in some sense intuitively or physically reasonably clear what it means. It's the amount of paint that you require to cover an area, or maybe it's the weight of a piece of the plane that you get once you cut it out. So we have this natural intuitive understanding that makes it easy for people to omit actually a careful laying out of the theory of areas. But when you actually look at it, you see that there are some interesting subtleties. So I'm just going to mention some of these. So of course we can start with the area of a rectangle. Area of rectangle, base times height. So assuming we already have a notion of distances or displacements. Area equals A times B. Then if we slice one of these rectangles like this, then we can get the area of a right triangle as A times B over 2. And then a little bit of combining these things allows us to generalize it to this kind of situation. We can say that the area of a triangle like this is the base times the height, now vertical height from the third vertex down to the base. A times B over 2 again. Okay, so that's fine. We can establish areas of triangles in this fashion. And then we get to a situation, say like this, where we have this triangle here. And now an interesting difficulty emerges, that the area of this triangle can be calculated now in a couple of different ways. One is to take the area of the rectangle, which we know, and then the areas of these 3 corner right triangles, which are like this, that we know. Take the difference, we get the area of that triangle. But another way would be to say, all right, let's choose this as the base of the triangle and measure that length. And then measure the altitude from this point to that base. And take base times height over 2. Now, is it obvious to you that the result of those two computations is the same? It's a theorem, right? You need to prove that kind of thing. You need, in other words, to prove that this notion is independent of orientation and that it's actually well defined. That if you cut something up in different ways and add up the areas obtained in with different rectangles or triangles, you're going to get the same number. So to put it another way, suppose that one person has a framework like this, X and Y like this, and they're very confident and happy about rectangles which are oriented in the same way as their axes. Okay? They're quite confident about calculating the areas of such rectangles. And then somebody else takes this coordinate system and rotates it somewhat, still the same scale, but rotated, and now this person over here is confident about the areas of rectangles that are oriented in this way. Okay, now we have some other region that we want to calculate the area of. So this person can use rectangles that are oriented this way and try to decompose it, and this person can use rectangles that are oriented this way and try to decompose it. And why in the world should it be that the number that this person gets is the same as the number that that person gets? Right? You see that there's some theorems here that require proof. Right? Of course we can say, well, it's just physically obvious. But our physical intuition is not enough when we're doing pure mathematics and we're trying to do it correctly. It's not enough to say, oh, well, it sort of corresponds to our intuition. We have to prove these things. So there's quite a lot of work, in fact, actually, to establish a proper theory of area along these lines. But unfortunately, the situation is more complicated than that. All right, so when we go to linear algebra, we discover that there's an alternate, seemingly different way of thinking about areas. So in linear algebra, we may have a triangle ABC, and we like to describe this triangle in terms of vectors. Maybe there's a vector u from A to B, a vector v from A to C. In terms of those vectors, the area of the triangle ABC can be defined as half of the determinant of A, B, C, D, where, say, the vector u is AB and the vector v is CD. A determinant here means A times D minus B times C. All right, so that's a linear algebra formula. It's actually a formula for the signed area rather than the area, because if you change the order of u and v, then the determinant changes sign. And so it's rather not the area of a triangle, but rather the area of an oriented triangle, which we might indicate by putting a little arrow here. So we're thinking about the triangle as having an orientation, whatever that means, ABC rather than ACB. All right, so we can then use this theory of signed areas of oriented triangles to build up a theory of areas or signed areas for more general polygons. For example, if you have a polygon ABCD, a quadrilateral, then we can think, say, of an orientation where this triangle is oriented that way and this triangle is also oriented that way. And then the area of ABCD, this oriented quadrilateral, could be defined as the area of the oriented triangle ABC plus the area of the oriented triangle ACD. Okay? All right, so one can define things like that, and then the possibility emerges of applying formulas like that to non-convex or twisted quadrilaterals like this. Right? If we have A, B, C, D in that order, then this signed area gives us an interpretation of areas in this context here. And this is quite useful if we want to have an additive theory of areas, so that if we have one polygon and then another polygon attached to it, that the area of the two polygons together is the sum of the individual polygons. In fact, if you want such a theory, you are almost forced to adopt the point of view of signed areas. Dealing with areas as positive is very, very cumbersome when you want to work with more general polygons. Is this relevant to calculus? It certainly is, because in many situations you will have a function that maybe dips below the axis. And then when you're integrating it, it turns out that you want to consider this area as positive and this area as negative and this area as positive. So it's essentially the same kind of business that's happening with these non-convex polygons. The same kind of business. So the point I'm trying to make here is that there really is a non-trivial theory of areas and signed areas. And that if you're going to do calculus properly, you really ought to learn this theory of signed areas before you start doing integration theory. It's just the logic of the subject. If you're going to think of integration as being built up from area. So the absence of a proper treatment of this subject in most calculus books is a serious logical weakness in modern calculus. It just is. All right, so we are now in a position, we've understood a little bit of the problems, some of the challenges in trying to pin down what this integral actually is. In our next video, we're going to resolve this question in a new and interesting way. In fact, a rather powerful way, which opens up many new doors for calculus. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.